Welcome to lecture 35. In this lecture, I will talk about how to set up quantum electrodynamics. Recall that in the last lecture, we found the action for scalar electrodynamics. In this lecture, we will disregard the scalar part of the action and just focus on the gauge field part, which was the action being 1/4 times the integral of a spacetime times FAB, where FAB is the field strength tensor that's built out of the antisymmetric derivative of the gauge field A. In this lecture, we will aim for constructing a quantum field theory using this classical action. Proceeding as with the scalar and fermionic field theories that we dealt with in the previous lectures, we attempted to write that the quantum field theory partition function Z is given as a path integral over the gauge field A times e to the minus of the classical action. Doing so, we can try to solve that path integral by using the fact that we can Fourier transform the gauge fields such that A is 1 over beta B, the volume, times a sum over all the wave modes in the different space-time directions over the Fourier coefficients, which we denote as A twiddle. Plugging this result into the Euclidean action, which is quadratic in the fields, lets us do the integral over spacetime. That gives us a delta function that lets us do one of the sums, so that we find that the Euclidean action is given as 1 over twice beta v times the sum over the Fourier wave vectors, and a quadratic action, which basically is such that we have a matrix k squared delta AB minus ka kb in the middle. The Jacobian from the Fourier transform from a of x to a twiddle of k is a constant, and as before, we may neglect it when we write down the path integral. The resulting path integral for the partition function is Gaussian because it's quadratic in A, so we can just perform the path integral, and we find that the is given as a product over all k times the determinant to the power of minus 1/2 of this matrix that we have in the exponent. So in principle, that's a well-defined result. There's only one problem with this. The problem with this result is that if we look at this action, if we look at the matrix that we have to take the determinant of, this matrix has a vanishing eigenvalue. You can verify this explicitly by noting that if we take the matrix and we look at the contraction with respect to the vector Ka, this just vanishes because delta AB Ka is Kb, and Ka times Ka is Ka squared, so that just cancels. So we get that this matrix has at least one vanishing eigenvalue, and if it has one vanishing eigenvalue, then the matrix is not invertible. The matrix is not invertible, the determinant of this matrix is 0, and we cannot take the determinant to the minus 1/2 power for the partition function Z. The naive version of quantum electrodynamics that we try to write down diverges. It's easy to see the reason why this happens. The reason has to do with the gauge transformation, or rather the invariance of the action under gauge transformations. So recall that SE is invariant under the local gauge transformation A goes to A minus derivative of an arbitrary function alpha of x. And in our path integral, we integrate over all functions A, or all fields A. So that means that there are a large number of gauge field configurations that have the same action SE because they all correspond to a class of gauge fields that can be found under these gauge transformations. So that means that since there are many gauge field configurations that correspond to just a gauge transformation, we have that there is a part of the partition function that is just an integration over all gauge field configurations alpha, and the action for all of these is constant because SE does not depend on alpha because of the invariance of the gauge transformations. So we find that the partition function has a contribution where we integrate over alpha times a constant. And of course, the integral that's unbounded over a constant is just a divergent contribution. This is the reason why the partition function diverges. Of course, there are ways to deal with infinities. We have learned about renormalization in this class. One potential way to regulate the divergence is to compactify the range of gauge parameters. So instead of considering the gauge parameter function to vary from -infinity to +infinity, we could compactify the interval such that it only ranges from minus lambda to lambda, where lambda is some finite constant. This resulting theory that we get from compactifying this interval is known as compact U1 gauge theory. And this can be studied non-perturbatively, for instance, using Lebesgue gauge theory. It has some interesting properties. For instance, it has the property that photons in this setup are actually directly self-interacting. This does not seem to be occurring in nature, where any interaction of photons has to be mediated by electrons. So it seems that this compact U1 gauge theory that we get or can write down does not actually correspond to the actual realization that we have for electromagnetism in nature. Partly for this reason, we will study a different way to repair the problem of the divergence that results from gauge transformations. So we found that the problem of the divergent Z is a direct result of the invariance of the action under gauge transformation. Straightforward to weigh out is to just say, well, then let's just break gauge invariance. So we could choose a gauge condition, which I formally write down as some condition G that is a functional of the gauge field A equals 0 that fixes the gauge. Examples for such a gauge condition could be G of A is A naught, so that would correspond to the gauge condition A naught is 0, which is also known as the temporal axial gauge. Or it could be DI AI 0, the Coulomb gauge, or DA AA 0, the Landau gauge, or any other sort of gauge configuration. So if we start by considering a path integral for Z that only is a path integral over gauge inequivalent fields, A bar, then if we write down the partition function this way, because all of these are inequivalent under gauge transformations, this partition function is not divergent. We don't double count, we don't have any infinite contributions from these gauge orbits because every inequivalent configuration is counted exactly once. We can stick in unity in this expression by integrating over the gauge condition G times the delta function of G. So this is obviously unity, and we don't change any of the other expressions. So this is the same expression that we had in equation 35.10. Now changing variables from G to the gauge parameter alpha. So instead of integrating over G, we have an integral over alpha times the determinant or the Jacobian from going from G to alpha. And the rest of the expression for the partition function is still the same. The path integral over the gauge inequivalent configuration is A bar, and the path integral over all gauge transformation parameters, that is the same as integrating over all gauge fields. So instead of writing path integral dA bar d alpha, we write just path integral over dA, where A is now the unrestricted gauge field. Similarly, because the delta function of the gauge condition restricts the integration only to those values of A that are within a certain gauge that's specified by G, we can replace the action that is a function of only the gauge inequivalent gauge fields A bar to all A's, because the delta function will take care of all those that are in principle integrated over and restrict to only the gauge inequivalent ones. So we've used a delta function that restricted G of A to be 0, but that is maybe overly restrictive. We could just as well have used the sort of restriction that g of a is f, where f is an arbitrary but gauge field A independent function. So instead of writing delta g of a, we could have written delta of g of a minus f, and none of the argument that I've given on the previous slide would have changed. Since any function f does the trick, we could average over all f's. And since we can average over all f's, we can also average over all f with a certain weight. We use Gaussian weight for f. We can write down the gauge fixed partition function that is a path integral over all a's, a path integrals over all f's, the delta function that restricts to the gauge condition, and the weight function e to the -1/2 psi times integral over f squared, a Gaussian weight, and the usual action. Psi here is an arbitrary parameter that will let us test whether our procedure is really really such that we don't change the physics. So basically, psi is an arbitrary parameter. If there was any result that would depend on the gauge, it would be unphysical. And if we find a result that depends on psi, that will tell us that there's something wrong with our result. So all physical results must, by construction, be independent of this unphysical parameter psi that we've introduced. Using the delta function, delta g minus f, we can actually perform the integral. And we find that this is given as the integral of path integral over a times the determinant times e to the -1/2 psi integral over g squared instead of f. So what we find is that we write the path integral as a that we write the partition function as a path integral over a times an exponential of something that could be an action. So this is our action that we had before. There is now an additional piece in the exponent. We could consider these two pieces to be part of a new action that is in the exponent. So that would not change much of the discussion we had previously. But we have this determinant in here that doesn't look like it is an exponent. So from this point of view, we would like to get rid of this determinant or rewrite the determinant. So, okay, so the path integral looks like an exponential, which is similar to the path integral that we had for scalars and fermions. The sort that we still have is this determinant, but we know how to write a determinant in terms of an exponential. We have learned about Grassmann integrations, so we can formally write down the partition function as a path integral over a and two Grassmann fields. Let's call them c bar and c. If we do this, then we can have an exponent that is c bar and c times a certain function such that the path integral over these two fields will just give us the determinant of this function dg by d alpha, which is nothing else but the determinant that we had in the previous expression. So using these Grassmann fields, we can write determinant formally as an exponent so that we have now a new expression for our action. These new fields, C bar and C, these are called Fadeev-Popov ghosts, and they are not real fields because really they just come from this mathematical trick that we want to write the determinant in terms of an exponential. Unlike the fermion fields, the ghosts are Grassmann, but they fulfill periodic boundary conditions in the time-like directions. So just like scalar fields, but they are anti-commuting. So they are sort of a field that is not really realized in nature. It is not a real field. That's one of the properties that they have. They are ghosts, but they're called ghosts for partly this reason. We will go ahead and then solve the gauge fixed partition function that I just wrote down in the next lecture. But as a sort of preview, I want to point out that including meta fields, such as the complex scalar fields that we had in the last lecture, or the electron field psi, does not actually change the procedure of these gauge fixing and Fadeev-Popov ghosts that we just outlined. So as a consequence, we find we can actually write down the quantum field theory expression for the partition function for quantum electrodynamics. It will be given as a path integral over the gauge fields A a path integral over the spinors psi bar psi for the matter fields, and this is missing here, a path integral over the ghost field C bar C. And then we have an exponent of minus all the contributions to the action. There is the matter part, which for real electrodynamics would be given by the fermionic fields psi. There's the gauge field part, which is just 1/4 FAB FAB. There's the gauge fixing part, which is just integral over the gauge fixing condition squared times 1/2 psi, where psi is this arbitrary gauge fixing parameter. And finally, there's the ghost part, which is the expression that involves the ghost fields C bar and C and the derivative of the gauge condition with respect to the gauge parameter alpha. And we will talk about how to solve QED in the upcoming lectures.